Hello everyone and welcome to this presentation. My name is Ali Bounab and today I will be presenting a work regarding geological control on landslides distribution in the rift chain, northern Morocco. The plan of this presentation is as follows. First, we will introduce the subject, then we will talk about the geology of the rift mountain chain, the methodology used in this study, the results, a synthesis, and finally, a conclusion. In fact, the rift chain or the rift belt is characterized by an abundance of landslide processes. This observation was made since the late 1960s and was confirmed by later studies. However, despite the fact that these researchers discussed the statistical association between landslides and tectonic structures, a clear relationship between an explanatory model of this association was never proposed. Hence, in this study, we will try to investigate the relationship between geology and landslides distribution, and we will try to propose a model to explain this statistical association that was reported by previous researchers. But first, we will talk about the geology of the rift mountain chain. In fact, the rift mountain chain is part of the Biticorifan chain. It's part of the Biticorifan chain, a chain which is characterized by the presence of similar tectonic units on both sides of the Alboran Sea. One of the characteristics of the chain is also the pure compression in the external domain and the presence of a mixed compression regime in the internal domain with compressive structures and extensional structures, which explain the creation here of the Alboran Sea basin. Platt 1989 proposed a model to explain this situation. In this model, around 27 million years, the compressional stress caused the creation and the surrection of the Biticorifan chain. Around 19 million years, the thickened lithosphere collapsed and a phase of extensional deformation began. Now, the compression resumed, but extensional deformation and indices for extensional deformation can still be observed. Romani 2014 tried to map geological structures related to the different deformation phases of the rift chain. According to this author, the Aquitano-Burdigalian transition corresponds to an extensional deformation period related to the exhumation of septid units. In the late Burdigalian age, an east-west compression is developed, and we have the activation of strike-slip faults and thrust faults. During the Miocene, the middle Miocene and late Miocene period, a north-south compressive regime is observed, which is responsible for the activation of many strike-slip faults and also the some thrust faults at the area, especially that of the Jibha, which is one of the major structural tectonic structures at the area. And finally, during the late Mycenaean Pliocene transition, a an extensional deformation occurred, which is related to normal subvertical normal faults that can be found alongside the reef coastline. It is also important to note that the internal domain and the external domain are different from a lithological point of view, because the lithology of the internal domain is mainly compact rock and metamorphic limestone rocks, compact rocks, while in the external domain we have fine-grained sedimentary rocks of the Tangier unit and flysch facies of the Napflysch unit. So to sum up, two types of tectonic structures are observed in the rift chain: post-Burdigalian compressive structures and late Miocene to Pliocene extensional deformation structures. In the external domain, of course, no evidence for extensional deformation was reported. But in the internal domain, we have a mixed regime of extension and compression. From a lithological point of view, a significant contrast is observed alongside thrust faults. Why? Because, first of all, thrust faults are areas where we have the contact between the internal domain blocks and the external domain. Also, the paratectonous Tangier unit is mainly formed by fine-grained sedimentary rocks, while the internal domain and the Flysch domains are formed by more compact rock types. Now we will discuss the material and data that we used for this study. So we chose two areas. The first area located in the internal domain, and the second located in the external domain. And then we conducted a landslide inventory. We prepared a landslide inventory map using a set of aerial photographs, because despite the recent advances in technology, we can clearly see that the performance of such methods is not sufficient. So the visual interpretation of aerial photographs is still considered the best tool for landslide inventory mapping. The sets used date back to 1955, 1958, 1965, 1986, and 2010. From this date onward, we used Google Earth imagery, and also we conducted field investigations to fill, the gaps in the map and to look for further information. To process the data, we used descriptive statistics and explanatory statistics. First, the landslide inventory map is transformed into a 10-meter resolution binary grid, which is compared to a 10-meter resolution distance to fault grid through the scope of frequency ratio and weight of evidence analysis, which allows to characterize the statistical association. Also, the landslide inventory map is analyzed using descriptive statistics, which produces weighted histograms that allow to understand the type frequency distribution, and both results allow the characterization of the geological control on landslide processes. Field investigations, of course, are also used to further investigate the statistical associations and propose an explanatory model at the end of this study. Now for the results, the explanatory statistics. So for the internal domain, we have 5 categories of distance to fault, to normal fault. For the first categories, which are all close to the fault, we can see that the FR value is superior to 1, which indicates proneness to landslides, while the fifth category, which is the rest of the study area, is inferior to 1. Weight of evidence results also confirm this because the C value is superior to 0, which indicates also proneness, and the results show that landslides follow the spatial distribution of normal faults in the internal domain. In the external domain, the same is observed. However, we are not talking about subvertical normal faults. We are talking about thrust faults, subhorizontal thrust faults, and it would also seem that landslides follow the distribution of the spatial distribution of thrust faults. As for the typology, one can clearly see that, here, must move here because that's better. So one can clearly see that the histogram bars in red are different from the other histogram bars which characterize the external domain. In the internal domain, we have a dominance of deep slide processes and rock creep, slow-moving deep-seated landslides, which are not existent in the external domain, while for the latter, we have a dominance of complex earth flow slide or complex earth flow slides processes. This is due to the lithological contrast between the two domains, and also to the deformation contrast and differences, which will be interpreted in the following slides. Now we'll present some field investigations and some site-specific studies to investigate this association. So the first example we have here is the Ras Mazari landslide in the internal domain, where we can see that the geometry of the landslide perfectly follows the distribution and geometry of normal faults, which indicates that normal faults initiate the gravitational deformation. Also here, a panoramic view of the Ras Mazari landslide proves the same thing. We can see here that the landslide is bounded to the south-southeast by a normal fault. We have here slow rock creep, and the material, which is a deep-seated gravitational deformation initiated by normal faults. Another example here is the Tamarnout landslide, which is also bounded to its north-northwest by a normal fault. And we have here a much more advanced weathering processes. We have thick colluvium and saprolite material, which are not seen here, but will happen if we give this landslide enough time. And we can also see other normal faults, which are related to extensional deformation and characterize this area of the rift chain. Another example of extensional deformation is presented here, close to the Tamarnout landslide. It's simply another shot of this normal fault plane, and we can see clearly here that the evidence for extensional deformation is very obvious. A third example is the Tamigart landslide, which is a subject of a recent publication by Bounab et al. 2021, where we can see here that the presence of a thick saprolite material and colluvium layer, but we can see here that the sea erosion action eroded a part of that, and we can now see again the bedrock outcrop here. So this is a more advanced stage of slow gravitational deformation. Here we can see evidences for marine erosion. We can also see here evidences for deep-seated deformation, where the wave cut platform is back tilted. And we can see here that the evolution for this landslide is not of rock creep type, but it's more of a rotational deep-seated slide. ERT results also confirm the observations, and the horizontal resistivity variations confirm the fact that we have a contrast here at the headscarp area, which indicates that the gravitational deformation was initiated by normal faults. In the external domain, we have an example of a recent landslide in 2018. And to interpret this landslide in its geomorphological setting context, we have here a landslide, a map of landslides along thrust faults showing the position of the 2018 occurrence, which indicates that this event in fact is just part of a multi-generational, multi-date landslide activity, very old, that takes place close to is in fact influenced by the lithological contrast alongside thrust faults. Fandaq Ain Jdida is also another good example of active landslides, where we can see here landslide scars in 2009, striated landslide surfaces, and when we look at this from a geological scope, we can see that this area also corresponds to a thrust fault, which is where the Benider flysch is overlapping the underlying fine-grained Tangier unit. A third example, which was also the subject of a recent publication, is the Ain Hawzi landslide, which took place in the Inchefshaun city, a city that is built practically on the contact area. And once we zoom in on the Ain Hawzi landslide, we can see that the landslide is also part of it's a partial reactivation of an old landslide that is practically located alongside the thrust faults. This landslide, of course, affected an urban area and caused a lot of economic damage to the population. From a lithological point of view, the inclinometer results, borehole inclinometer results, show that this landslide is in fact corresponds to the stratigraphic boundary between scree deposits, old scree deposits, and underlaying non-weathered clay material. And how the ART investigations and surveys also confirm this, where we can see here that the landslide body is practically just made of scree deposits, which are sliding along the underlaying clay material, plastic clay material. So to sum up, we have here a synthesis, a model for the landslide instability in the rift chain. In the internal domain, we have during the late Miocene, Pliocene era or age, an initial morphology that is mainly controlled by tectonic activity, where we have normal faults creating here many metric to decametric scarps. Then these the material starts to slowly creep downhole during the reswoon period, which was characterized by extreme precipitations, and the superficial layers began to suffer from chemical weathering processes. This we can call the Tambernut stage, since the Tambernut and Ras Mazari landslides are still practically in this stage. A more advanced process, which is attained by the Tamegart the Tamegart landslide, so we can call this the Tamegart stage, where the weathered layers become so thick that the landslide starts evolving into a deep rotational slide. For the external domain, we have the slope instability processes are mainly controlled by thrust sheets and the contrast that they have with the underlying clay material, fine-grained paratectonous tangerianate. So the first scenario we have is a scenario where during the reswoon period, the extreme precipitation caused the exertions of many water sources here, which started to saturate the soil layers here and created deep, slow-moving earth flow processes, which then evolved into complex landslides or evolve into slow earth flows and stay slow. The second scenario is a scenario where the front of the thrust sheet collapses and we have thick mixed colluvium and scree layers, which then become subject to complex landsliding processes and suffer from rotational simple slides and flow-like slope instability processes. So, in conclusion, one can say that the findings of this study emphasize the role of geology in determining the spatial distribution in typology of landslides, since we can now explain much of the slope instability processes simply by the geological structure of the area. But we think that bigger samples should be used or can be used in future studies to verify the findings of this research. And also, one can also use morphometric indices to study the vertical displacement of tectonic origin and its relationship to landslides to further confirm the findings of this research. Thank you very much for your precious time, and I think that's it.